And what Einstein says is that there's two rules to his postulates. The first thing is that the speed of light is constant regardless of the motion, regardless of how fast you're traveling. So let's say if you're in a spaceship that's traveling at 0.8 c, this basically means 0.8 c means that you're traveling at 80% of the speed of light. If you just if you shine a flashlight in this direction, the light is not going to travel at 1.8 c. The light will travel at the same speed of light, which is 1 c. It doesn't matter how fast or how slow you're going. The speed of light is always the same. The next thing is that, like I said before, the laws of physics are the same in all inertial or non-accelerating frame of reference. Where the reason why we say non-accelerating is because when things start to accelerate, that's called a non-inertial frame of reference. And when that happens, we get into something called general theory of relativity. And that stuff is very complicated. Let's just say that you need a master's in physics just to understand what general relativity is. So that's why in VCE Physics, we just stick to the special relativity, where things are non-accelerating. Go on, skip this. And this is why Einstein's postulates are important. So here's the thing. We have this scenario where we have an atomic clock on Earth and we have an atomic clock on this rocket ship. An atomic clock is basically a tube where you have some electron that just keeps bouncing up and down, up and down, up and down. And like for the sake of argument, let's just say that one up and down is about 1 second. So here's the thing. When you're on Earth, the clock, like this up-down motion of the clock, is going to work as expected, right? Because you're next to the clock. It's just going up, down, up, down, up, down. But the thing is, from your perspective, when you're looking at the rocket, this sort of electron, or like the clock, is traveling a longer distance, right? So let's just say that in 1 second, let's say it travels, like the light travels 1 meter. 1 meter. When you're looking at the rocket, since the rocket is traveling, you can see that the electron is traveling a longer distance, right? So in 10 seconds, let's say in 10 seconds, the electron will travel 10 meters, like according to us on Earth. So according to us over here, the electron is going to travel 10 meters, up, down, up, down, up, down, right? But when you're looking at the rocket, what's happening is that since the rocket is traveling, you're going to see the electron travel a longer distance. So in 10 seconds, the electron has traveled, let's just say 15 meters. And the reason why this is a problem is because in the case of the rocket, light has traveled a greater distance in the same amount of time. And because we said speed of light is constant, then that's breaking the laws of physics, because light just traveled faster than the speed of light. But that's not the case. The reason that's not the case is because of something called time dilation. Yeah, I told you, this stuff gets very, very mind-boggling very quickly. Yes, essentially what's happening is because you see light travel a greater distance, time has to slow down. And then we get to this formula. It's a pretty ugly looking formula, but essentially time is equal to time zero times lambda. Lambda is just some number, and that number lambda is given by that lambda is called the Lorentz factor. And Lorentz factor is given by this 1 divided by v squared divided by c squared. Cool. So the bigger the lambda is, the bigger the time dilation is. And so first of all, you need to be able to differentiate between t0 and dilated time. And so t0 is what we call the proper time. So the time interval between two events in the same reference field where the two events happen at the same point in space. So if we're in the previous example, if we were calculating the amount of time it takes for the rocket to leave Earth and then come back, t0 would be the time that we measure on Earth. So let's say the rocket takes, let's say the rocket takes 10 years, according to sorry. Well, sorry. Yeah. Let's say the rocket is traveling to some galaxy and it's traveling to some galaxy and it's coming back. What the person in the rocket is trying to measure is how long did it take for him to go from Earth to the galaxy and back. So t0 would be the time that the astronaut measures, because he is in the same point in space as the thing we're measuring, which is the time it takes to go to the galaxy and then come back. So the astronaut would have would be time 0. And so what we experience is the dilated time. So let's say if the astronaut takes, so using this formula, let's say the astronaut takes 10 years, the Lorentz factor, let's just say it's 2. While it takes 10 years for the astronaut to complete his journey, from our perspective on Earth, that time is going to take 20 years. Right, so I told you, it gets very, very confusing. Yeah, I don't have enough time to explain this properly. But if anyone has watched the movie Interstellar, it's kind of the same idea. So we have the astronaut guy who travels somewhere in space. And because he's traveling so far, his time is slowing down. So while he only experiences like 5 or 10 years, the people back on Earth experience 100 years. And that's why when astronauts will go to space, they will age slower than us on Earth because of time dilation. Because they're traveling at such a fast speed, their time essentially slows down relative to us. Yeah, I told you. Very, very confusing stuff. And the second thing that can happen is length contraction. So while time increases, length is going to contract. And the way this works is, let's say we have some rocket that's 100 meters long. And let's say the rocket is traveling. The proper length, so the formula for this is L is equal to L0 divided by lambda, divided by Lorentz vector. L0 is the actual length of the rocket. And you can measure that if you're in the same reference frame as the rocket. So if the rocket's traveling, let's say the rocket's traveling at 0.8 c, if you are on the rocket, you're on the same reference field as the rocket. And because you're on the same reference field, you can easily measure the length to be 100 meters. But because we are the outside observers looking at the rocket, what we're going to see a contracted length. And instead of seeing 100 meters, we're going to see a rocket that's only about, let's say, 90 meters. And it contracts in the direction that we are traveling. So if the rocket is traveling in this direction, the length of the rocket is going to contract in the x direction. Cool. Hopefully your mind is not completely blown just yet. And the reason why this is important, it actually has some real world applications, and it has to do with GPS. And because satellites are up in space and traveling so fast, if the satellite does not take into account the time dilation, the difference of time between the satellite and the Earth is about 6 microseconds. And while 6 microseconds doesn't sound like a lot, if the satellite is out of sync by 6 microseconds, which is caused by time dilation, your position on the GPS will be wrong by a factor of 2 kilometers. So that just shows that like time dilation actually has some real world impacts other than just imaginary spaceships traveling at really fast speeds.